Hi everyone, welcome to the latest webinar with Fibre Systems. My name's Keely Portway. I'm the editor of Fibre Systems and I'll be your moderator today. In terms of housekeeping, we'll be around in about an hour, about 35 to 40 minutes presentation, maybe a little longer, and then we've got the opportunity for a question and answer session at the end. Feel free to submit your questions via the question box at the bottom. You can submit them throughout the webinar. You don't have to wait until the end. So don't be shy. Ask our participants some questions. So in terms of our topic, today we are tackling something that's moved from background infrastructure to more of a strategic variable, optical internets in AI training clusters. As these clusters scale to 100,000 plus GPUs, every decision about fiber, topology, cabling, it all now carries real system level consequences for training, speed, cost per GPU, reliability, the list goes on. And of course, hyperscalers are committing billions to this kind of infrastructure. So getting it wrong can be very expensive. So today, I'm very delighted to introduce our speakers from AFL. We have Antonio Castano, Market Development Director, Global Sales. We have Keith Sullivan, Director of Strategic Innovation. And we're welcoming back Ted Lucullus, Engineering Director. So I'm going to now hand over to Antonio, who's going to lead the discussion. Antonio, the floor is yours.
Thank you, Keely, and welcome everyone to this Architecting AI Networks at Scale with strong focus on training clusters. As Keely mentioned, I'll be driving through some market insights, market trends. Keith will take us on the innovation and architecture side of things, and then Ted will be covering some of the technology trends that we are seeing in the marketplace. All in all, we are going to be around 30 to 40 minutes in explaining why AI training has outgrown conventional data center design. And now the decisions that needs to be taken carry a system level consequences. Now, there is some slides that will be more commercial market trends, as I mentioned. There will be some technical slides as well. So let's pay attention throughout the next several sets of slides. Moving to the next one, if there are 5 things here that you will take away, take this. Power decides geography. Right now, one AI training cluster needs around 250 megawatts, which is a power station's worth of electricity. So where there is power available, the bill follows. We have seen that in many regions across the globe, in the US, with, for example, Texas becoming a predominant area, or in Europe, we see the flap market as the main region in the past. Now,
Antonio,
yeah,
sorry to interrupt. You forgot to share.
I'm not sure. Sorry.
No.
Thank you, Keith. Well, sharing helps. So let me know if you can see the slides, please.
Not yet. Do you want me to put them up?
No, it's fine. I have done this before. Obviously, not very well.
Oh, there we go.
Okay, good. So let me bring this into slideshow. Can we see them well?
Yeah, good.
Yes.
Good. And apologies everyone for this. It's a shame it happens live, but we got it in our hands now. So luckily it was only the first slide. The 5 main things that you could be taking with you today. I covered the power. I was jumping into the optics now being the new bill of materials. A single training cluster can now have 700, 800,000 optical modules, 6 on the network for everyone that sits at the chip. Optics are now outdrawing the switches, so transceivers are burning more power than the switches they are being plugged into. So every optic decision is also tightly linked with a power decision. Architecture is cascading into millions, so fewer network tiers means less switches, or fewer switches means less power, lower risk, therefore less money. And these are all very large choices that needs to be taken into consideration. The fiber plan is the lasting asset. That's another main takeaway. While the chips are turning every 3 to 5 years, in some cases, this depends on the customers. A properly cable plan can outlive 3 generations of everything else that sits in the training cluster. Now, moving to the next slide on the workload shifts that we are seeing, the training data center has become a very massive orchestrated factory that is purpose built. Just to set a little bit the scale, ChatGPT alone has around 800 million weekly users inputting 2.5 billion prompts a day. Density has exploded. A single rack now draws 120 kilowatts, which is 12 times more than what high density was considered 3 years ago. It was around 10 kilowatts. And this is continuing to scale. AI optimized servers are now 21% of data center power today, and is increasing as well, heading to 44% by 2030. The IEA sees data center electricity demand roughly doubling from 24 to 30. Additionally, the unit of design has shifted from what it was a server in the past to a rack recently, and going forward to a pod as the scalable unit. Basically, multiples of rack within the same brain. Hyperscalers are committing hundreds of billions in CapEx AI infrastructure. The last time I checked, summing up all the CapEx announced by the hyperscalers for 2026, we are almost at 800 billion, and most of that is going to be focused on building AI infrastructure. 3 times the training workload is what we are seeing going forward. McKinsey model says that training compute will triple from 23 gigawatts today to 62 gigawatts by 2030. That's a 22% CAGR. There are two main levels driving it: adding more GPUs and adding faster GPUs. Both demand high performance interconnect. For example, optics. Gigawatt training campuses are already operational. We have a few out there: Meta, Prometheus campus, or XAI Colossus in the US. Multi-plane fabrics are the hyperscale default nowadays. Traffic is being sprayed across parallel planes to absorb all-to-all load. At a scale, planes win on resilience for week-long training jobs. Ethernet is running everywhere, both on the front end and the back end. And this is going to keep being the default fabric that is going to be using going forward. And then the decisive shift, DCI is becoming part of the training fabric nowadays, with parallel optics 800 CR at 120 to 2000 kilometers, stitches smaller campuses into one single virtual training cluster. So for every additional gigawatt, land as more optical ports, more single mode fiber, and longer, denser cable plans. Looking at the strategic difference between AI clusters, not all workloads are the same, and the difference decides where things get built. So cloud compute is what we have been seeing until very recently, 40 to 200 megawatts at 15 milliseconds latency between the regions, that is air-cooled, integrated into those cloud campuses. Inference AI, it's 50 to 250 megawatts, similarly or similar latency, 15 milliseconds between regions. Liquid cooling is being preferred, and they must collocate near each other to have data accessible. So it belongs more with the cloud assets, as we are seeing. But then training is carrying somewhere between 300 megawatts to 2 gigawatts, tolerating 100 plus milliseconds latency. Liquid cooling is required. As we said before, racks are now driving 120, 200 kilowatts. So it can't stand alone in a dedicated campus. Campuses with more than 50 megawatts and liquid cooling are the best position, and sites without risk, sites that without risk, material costs, and lower leasing yields. Here is a conceptual heart of the talk. Training clusters obeys to different physics. The traditional data center have millions of independent flows. A failed link will slow a function of the workload, but average performance is what really matters. On the AI training fabric, one job is shared across 100,000 plus accelerators, and every step in synchronization. So the slowest link is actually the one setting the cluster pace. So worst case is what actually really matters. So think about the following analogy, a relay race, where you have 100,000 runners who must all touch the button at the same instant. And the slowest runner is the one that sets the pace for everyone. So one slow optic doesn't slow part of the cluster. It is slowing all of it. Meta production data that we have gathered says a single flaky optic can cost 40% of the training cluster performance. So there are 4 different pressure points that we are seeing, 4 forces that are converging into the optical layer. Bandwidth per XPU, input output into the trillions of bits per second. Copper runs out of headroom before or long before AI does. And that's why optics are being considered for everywhere. Predictability, the worst case sets the pace, not the average, as we have just said. So tail latency is everything, and consistency is not beats the minimum latency. Topology, 100,000 plus endpoints can sit on a flaky network. Multi-tier closed fabrics with thousands of switches and hundreds of thousands of links. This is where the optical risk is concentrated. And then resilience. At this size, there is always something gonna be broken. So designs must be capable of riding through failure. Recovering time becomes a top-line metric because restarting a job that is halfway through is not an option. So if the optical layer is carrying all risk, how should we think about cost? Two clusters that has identical price tags can now deliver 2 times different results. The equation that is useful for training is chips TFLOPS times utilization times scaling efficiency times availability. Utilization is, we think of the real chip using only 35 to 55% of the theoretical peak. And most of the gap is network behavior, congestion, slow links, recovery time. Scaling, going from 10,000 to 100,000 accelerators amplifies every interconnect weakness that you have in the network. So the fabric's worst case is setting the slope. Availability, MTTR driven, and how fast you find and replace a failing link. This is critical in a training cluster. The commercial kicker, 250 megawatts running 24/7, lifetime energy bill matches or exceeds the hardware bill. The joules per token makes optics power a commercial question, not just an engineering one. When we look at the transceiver, and Ted will cover this a little bit later, there are different decisions that needs to be taken and questions to be asked. Pluggable, near package, or co-package optics, and which is the way to bet for. Pluggable probably today is field replaceable, multi-vendor, provides scale. On the other side of the coin, it has a higher power per port and a density ceiling at 1.6 terabytes per second. Near term, linear near package optics, it brings lower power, it keeps serviceability and incremental path for the future, but has a tighter integration and new failure modes that were not seen on the pluggable optics time. And then co-package optics, which is emerging. It has the best power and density, shortest electrical path, as we will see later on. And we have already some companies that are shipping and adopting CPO on the scale out. So the industry is bullish on CPO. There is going to be adopters and neglectors. It's important to be cautious, but to understand the reliability, but co-package optics will eventually get adopted in the field. When we think about the rack and the scalable unit, scale up, scale out, or scale across fabrics, we also think about the length of the different assemblies that we see. So on 0 to 3 meters inside the rack, passive copper is the cheapest and most reliable, lowest power at the moment. Still in scale up, but in the same pod, in a different rack, active optical cables, single mode fiber will be the sweet spot for this short reach. 7+ meters, we have single mode fiber in the structure cable plan alongside pluggable optics, and then obviously for DCI, whether that's campus DCI or metro long haul DCI, we will see fiber being critical there. So the permanent fiber plant outlives 3 generations, as we said at the beginning. Field swappable optics helps in repair, being minutes, not hours, and time is money in a training, in an AI training cluster. And then vendor independence. So having several vendors available so you don't get the plant locked with a specific vendor. Now, Keith, if you take us through architecture and the topology on an AI training cluster.
Thank you, Antonio. Um, I've swapped screens to mine, so hopefully everybody can still see the screen. Let me know if you can't. So yeah, I'm gonna cover mainly the why such an increase in fiber for AI clusters, and then a how and how we kind of build these clusters. So Antonio mentioned a few times a 100,000 GPU cluster. So this presentation I've given probably a year and a half ago, and I was talking about 64K clusters. So 64,000 GPU cluster. They've grown massively and they continue to grow. We built one in the US last year that was 160,000 GPUs. In Europe so far, I haven't seen any 100,000 clusters, but they're coming and they're coming probably this year. So I do have a lot of content in here. I'm not going to go into the detail. I'm just going to try and address the why to go through it quickly. And then for the build of the 100K cluster, I'll go through it quite quickly because we're already 20 minutes in. So I need to go through it pretty quickly. Um, so that slide move on. Yeah. So if we compare a traditional cloud server just to a H200 GPU node, and the H200 is nowadays quite antiquated. It's still used in some inference bits and pieces, but you wouldn't build a training data center on H200. This was just for a comparison of where we were 18 months ago. So a normal 1RU pizza box server, it's 60 cores, 700 watts, about 10,000, and then H200 had 8 GPU accelerators, and it's the massive number of cores that allow you to do all the parallel compute, which allows you to do the AI. And each one of these 8 GPU accelerators was 10.2 kilowatts and approximately 200,000, depending on who you are to purchase it. So then if you stick those into a rack, if you really pack out a rack with 1RU pizza box servers, you can get 36 in there. I have seen instances that they've had 36 in there. It's 5 kilowatts of power. It's on average in a hyperscale data center, 15 to 30 fibers per rack is pretty common. So you can have 576 fibers run to your leaf switch in the middle of the row, and there could be anything between 20 and 40 racks in the row, which gives you 15 to 30 fibers per server rack. And the cost of that whole rack is about 200K. And then on the right-hand side, we have two H200s. The DGX H200 is 20.4 kilowatts of power, so 4 times more. And there's 144 fibers. So each GPU, each DGX has 16 MPOs for the back end and 2 for the front end, and the total cost is 400K. So that was already a significant increase. And even the reason why only 2 DGXs in the rack, if I put 4 in there, which you can do, then you're up to 40 kilowatts of power, and cooling that is going to be a serious challenge. So if you're sticking with traditional air cooling, you get 2 of those in a rack, and that was pretty common deployment. So at that level, that was a pretty stark jump from your traditional cloud to your DGX. And if you take it up a level to the NVL72, which NVIDIA announced year and a half ago, this was the first single rack scale GPU node. So call it a node because it really behaves as one single GPU. So there's 72 GPUs in the whole thing. They're very tightly linked with the NVLink switches, which are the ones in the middle, slightly different format you can see of the shelves and the rack on the left. And then the NVLink, it's all linked with a copper cable in the back, which you can see kind of going up the back of the rack on the right. That's the back side. But it's in total, it's 125 kilowatts of power. It's about 2.5 million. And there's let me go to the next one. Then comparing the DGX H200 to the NVL72. The NVL72, the Grace Blackwell 300. The Grace is the CPUs, so there's 36 CPUs, and the Blackwell is the GPU, there's 72 GPUs. And then the 9 NVLink switches, so there's 1152 fibers per rack. So we've gone from the traditional cloud server that had between 15 and 30 fibers per rack, and now we're dealing with 1152 fibers in one rack, which is 144 MPOs. It's all, when NVIDIA announced it, it was there was a lot of discussion still on liquid cooling, whether it would be direct to chip or immersion or a sidecar or a rear heat exchanger. And NVIDIA just announced this and said, oh, by the way, it's a direct to chip liquid cooled. So that was the de facto standard in the market then. Excuse me. And this is just to have a look at the scale up, what we call scale up. And the majority of the presentation I'll focus on scale out, but just had to cover scale up. So scale up is what actually links all of the 72 GPUs into effectively one synchronous GPU in the whole rack. So there's about a mile of copper cable in the back of the rack. There's 1,296 connections across the 9 144 ports per one new switch. That's all blind mate, and it's all cable bundles currently, but that's going to move to a copper mid-plane in the near term, and longer term, probably 3, 4, 5 years out, we'll see optical in that backplane or mid-plane in the scale up. In the meantime, it'll stay copper because of the speeds and the distance. Copper can kind of handle it. Okay. So that's the why. So the why is basically because we've gone from 15 to 30 up to 1152 fibers per rack. And now it's how on earth do we cable that up and how do we build a 100K cluster? I will go through these pretty quickly. There's a lot of just quick slides, but it's just to give you an idea of the size and scale of a 100K cluster. Because a 100K cluster is a pretty significantly large cluster. So we start with a single NVL72 rack. And the blue in the corner is my rack position on the floor. It's pretty straightforward. We've gone through it all before. It's 144 MPOs and 1152 fibers. That's our first node, and that's 72 GPUs, Blackwells. So then we build out a row. We put 8 of them in the row, and even though they're now liquid cooled, they're still generally deployed with a single rack space between each of the racks. Originally, the rack spaces were there to allow more air cooling, but it's the one thing that's not constrained in an AI data center is space. So there's generally plenty of space. There's not enough power, there's not enough cooling, but space there's loads. So once I put 8 in here, now we're up to 576 GPUs per row. We've got 1152 MPO connections, whereas the previous slide we had 1152 fibers, and now we're up to 9,216. And this, I just have to highlight, this is a very generic 100K cluster that I just developed, and I developed it with just trying to do multiples of 8s, which makes sense. So then after you build your first row, then you put in some T0, and a T0 switch is basically the same as a leaf switch or a whatever, but you can call them BT0 switches, which is back-end T0 switches, or leaf, or whatever you want. But you put in the 2 switches, and then all of the GPUs will cable to the 2 switches. So the the orange and the red give 2 sets of spines, and in the T0 there's a 2,304 MPOs total. It's 18,342 fibers, and they're south facing, north facing. So you can see even in one row how the fiber count increases very, very quickly. So then if we look at the going down, if we have, for feeding down, we're feeding 1152 fibers from each of the blue racks into each of orange and each of red. So there's 576 to orange and 576 to red, or to green. So running them down, the easiest way is to run. You could run 144 fiber, or sorry, you could run MPO patch cords down the row, but basically you'd be running for each GPU rack, you'd be running 144 MPO patch leads, or you can run one single 576 fiber trunk to each of orange and red. So total of two 576 fiber trunks, or 144 MPO patch leads. On the left there is just a table of the different options for this. This is our most compact cable that we offer. So this is based on a spiderweb ribbon. It's very, very tightly packed. So we have a 9.5 millimeter 288 fiber cable, or the 576 is a 12.4 millimeter diameter. So running, ideally, the rule of thumb for building an AI network is you want to increase the fiber count as high as you possibly can in order to reduce the number of cables that need to be installed and the number of cables in the basket. So the cables in the basket grow extremely quickly. So if you can increase the fiber count and reduce the OD of your cable, that's the most efficient way of installing it. So in order to install very high density, the first thing we do is we increase the fiber count, we reduce the cable OD as much as we possibly can, and then we have to get much more dense on the fiber connections. So in most of the large AI data centers, we've migrated already over to the MMC connector. So the MMC connector, it is available as a 1x12, a 1x16, and 2x12. I've never actually seen a 1x12. Majority is 1x16, and one customer uses a 2x12, a 24 fiber, with 2 rows of 12. It's push-pull, it's very high density. It's now available from a much broader number of customers. A year and a half ago, it was constrained. Now we're terminating. I think this year we're going to terminate about 12 million MMC connectors. So they're pretty common now and in complete mass production. The ferrule itself is what we call we have the MPO in the top right. That's the MPO 16. You can tell it's a 16 because the key at the top is offset, and obviously there's 16 holes if you want to count them. But the ferrule side of a MPO connector was the MT, which is the mechanical transfer, and that was originally developed by NTT and Fujikura, which is our parent company in Japan. And then it's been around now for about 25 years, I think, more than that. And then the MMC is based on the TMT, which is just very simply the tiny MT ferrule. So we reduce the size of the ferrule, which then allows you to reduce the size of the connector. And so you actually fit 3 MMCs into the footprint of one MPO, which allows you to pack way more density. So this is just one example of an MMC panel we developed. This is a 1RU, and it's 1536 fibers. So this was developed for an application where we were terminating 768 fiber trunks. It was MPO at the T0 and MMC at the T1. We can pack an awful lot more density into a 1RU. We have done a 3456 fiber 1RU panel, but that's reaching the physical space dimension, but it way exceeds what's manageable. And what's important here is the balance between manageability and density. There's no point in putting in a panel that has 3456 fibers. So it was 54 quads in one panel, and it's manageable to put it in, but it's not manageable to manage the fibers through the life cycle of the data center. So in order for this particular panel, the application we installed, it was 1536 fibers, and the original requirement, we had a patch rack, and they wanted only one patch rack. And I calculated it out, and it came to, with an MPO 8, it required 112 RU of rack space, which would have been a rather tall rack in a data center. So we moved it to MMC and we brought it from 112 down to 28 RU. So you can see there the immediate impact the MMC connector has in a panel that I view as low density for MMC. So once you're putting all these fibers in, you have to have solutions that allow you to put way more fibers into patch racks and solutions at the top of switch racks or top of the server racks. So then another option we've done recently is a MMC called ultra high density patch rack. This was a solution the customer asked us to do, but I said it's just not going to work. So we developed this. This is you can get it up to 73,000 fibers in a 1200 by 1200 floor space. So you can either fit in 128 576s or 64 1152s, or you can go on up and it gets to 31 34 56s. So it has the cable management that allows you, even when it's fully populated, which is the picture on the right, well, both pictures. When it's fully populated, you can remove a single cable if you need to, and it has slack storage in the back for we wanted 5 meters for 160 cables coming in. So that gives us 800 meters of slack storage for a 576 with an OD of 12.4 millimeters. So it's really all about making patch and dense solutions that are still very manageable. So there's no point in cramming in as much as you possibly can. It has to be manageable and still be able to install it, and still simple and intuitive to install. Okay, so coming back to building, this would be your GPU to your T0. You could come out of the rack to a patch panel overhead, and then you would patch it onto an MMC connector, and then run two 576 fiber MMC trunks to your T0, one to each T0, and then you would patch from an adjacent rack into the T0 rack. So you can still direct connect if you need to, if you want to, but most people are now choosing to do a patch and high density patching solutions on each end. So, and the 576, because we're coming out of the rack here with 1152 fibers, and we have to go to two T0s, the logical highest fiber count we can go to is a 576. And that's what we want to try and achieve all the time, is to get to the highest possible fiber count that's still manageable and achievable without doing anything crazy, jumping between racks. So then after we built out our first row, we build out a power pod. And again, I've just put 8 rows in my pod to keep it easy. So this is my GPU count now gone from 576 up to 4608. So you can see we're increasing, but we're still nowhere near 100,000. And now we've grown to 9,216 MPO connections. So that's MPO links. So it's 18,000 MPO connectors. There's 72,000 fibers. And I think I took the average length of these at about 13 meters. So that gives you 1,180 kilometers of fiber in one pod. And that's just connecting the GPUs to the T0. Okay, moving on. So then after we build our first pod, in order to grow that 4,608 GPUs in one pod, you do the maths, you got to grow it to 22 pods. So this is what a 100K cluster would look like with the amount of GPU racks. And at 2.5, each of those blue cells I said was $2.5 million and 125 kilowatts. So you can do the math pretty quick on the cost of that data center and the power required. So here we've got 22 pods. 22 pods gives you 101,300 GPUs. There's 202,000 GPU to T0 MPO links, which would equate to 2,816 576 fiber trunks. So you can see the need for managing that fiber, need for reducing the cable diameter, need for reducing the cables that you install and the time you install. That's all absolutely critical, because every hyperscale that builds one of these clusters, the most important thing they want is of course, the fiber is the last thing that goes in. So it's the last thing standing in the way of switching that data center on. So we get immense pressure always to make sure we can deliver it as quickly as possible and that the cable can be installed as quickly as possible. Because if we save a week of installation time, it's nothing to do with the labor cost of that installation time. It's the revenue or the training that they can do a week earlier would pay for the entire fiber infrastructure. Okay, so then once we've done it, we've only connected now as far as our T0s. So we need to get a T1 network switch rack. So the T1 network switch rack is generally at least twice the density of a T0. So here I put in multiples of 16. I put in 16 2RU 800 gig switches, which is 128 MPOs per switch. So it's 2000 MPOs per rack. Generally on the T1, between going south down to the T0 switch and going up to the T2 switch, there is contention. In the GPU to the T0, there's no contention. It's full non-blocking, so it would be half down and half up. This has a contention of a 3-to-1. So of the 64 OSFP ports, you have 48 going down to the T0 and 16 going up. So in total, it's 16,000 per T1 switch rack, and there's 2 cores, each with 64 T1 racks. So the core would look like this. That's our 8 rows of 8 racks, 64 T0 switches, which gives us 98,000 south-facing T0 MPO links and 32,000 north-facing to T2 MPO links. So it's a total of 786,000 fibers, which I think for that I calculated 113 meters average length, gives you 88,000 fiber kilometers going from T1 to T2, or sorry, T0 to T1. So then you've got your core, you put your cores into your cluster, and then your final cluster is your 22 pods, your 2 cores, your orange core and your green core. And obviously all the orange T0s go to the orange T1s, and the green T0s go to the green T1s. And then I've left out the T2 core because that's really outside of the cluster. So there's our 100,000 GPUs. We've got 202,000 GPU to T0 MPO links. And then because it's non-blocking, you also have 202,000 T0 to T1 MPO links. So if we just normalize it on 576 fiber trunks, that'd be 2,816 each layer. And there's 25,000 fiber kilometers in the GPU to T0 and 182,000. So we're looking at over 200,000 fiber kilometers in 100,000 GPU cluster. And that is it at lightning speed. So I'll hand over now to Ted Luchulis, who's our engineering director. He's going to go through some of the technology trends we're seeing that are enabling all of these clusters.
Thanks, Keith. You could advance to the next slide. I'll move fairly quickly since we're getting fairly late in the time. But really, I'm going to hit at a high level some of the technology trends currently and maybe just a little bit of exposure, focusing on some of the kind of higher density connectivity and the transition from copper to ultimately co-packaged optics. So in this slide, I'm just breaking it out, the scale up into vertical and horizontal, the scale out, and then the scale across, and kind of pointing out the key aspects. So within the current technologies, within the scale up and the vertical scale up specifically, it's really dominated by copper with a copper backbone. And in the horizontal scale up as connecting kind of multiple adjacent racks in the nodes, it's off the switches will be pluggable optics. As you work into the scale out, it's as Keith had talked about, dominated by the switches with a pluggable optics with a structured single mode backbone. And then the scale across is moving kind of outside the data center, really connected with coherent modules and maybe the ZR plus modules. As you move into the emerging technologies, I think as you move from kind of the left-hand side of the slide to the right hand of the slide, you're going to start seeing implementation at different times of some of the co-packaged optics in the transition from maybe purely kind of electrical equipment to some of the integrated silicon photonic switching, and then also introducing other types of fibers in the scale out with the need to increase density with a significant amount of cable space and fiber space that's taking up. The industry is exploring potentially using multi-core fiber to help reduce that density. And then as you get into the scale across space, industry is evaluating hollow core fibers to also help reduce latency between data centers. Okay, next slide, Keith. Okay, just it was kind of talked a little bit in Antonio's discussion, but just sort of what is driving the transition to co-packaged optics through its various steps. And you'll hear this term, the copper wall. So there become physical limitations on kind of an electrical trace as you start increasing the data rates, how far you can transmit without significant signal loss. Okay, as as electrical traces of up to 224 gigabits are being implemented, the rate at the distance at which you can transmit along copper is being reduced significantly. Okay, there are ways to extend it, and you see this within racks by using active electrical cables, but we're starting to approach a physical limit. So as you start implementing different phases of optics directly, you're overcoming some of the signal loss issues, but you're also starting to get other secondary benefits. Okay, one of them is that you're getting a reduction in power in the data center. And as Keith had talked about, there's a substantial amount of power draw in the different data center architectures, but also within just the basics of the signal transmission, the optics allows you to get closer to your compute chips and then potentially starts locally on the board level, increasing your bandwidth. Next slide, Keith. Okay. So just briefly kind of going through the evolution of the optics, and I won't spend, I'll just talk about some of the key points and just to go through. So the current workhorse is obviously the pluggable optics, like a transceiver that's being plugged in. With a cable assembly, there's some sort of electrical optical conversion, and then ultimately signal traces to the ASIC. Onboard optics is kind of the next intermediate step where you're replacing the transceiver, where you have some sort of optical connectivity on the front of the kind of the equipment. And you're now doing, instead of a discrete object, you're doing this optical electrical conversion on the board. Okay, Keith, next slide, please. Okay, and this is where you start getting into the implementations that we're seeing now. So there's a near packaged optics and a co-packaged optics, and they're very closely related. So the near packaged optics is, I think, being adopted by a number of different people, but it's bringing a silicon photonics circuit to a kind of a same substrate that you're seeing with the ASICs. There's still electrical connections, either directly on the board or with a connector, but it's providing a good manufacturing option of combining the optical connectivity on the board with some of the electrical kind of the chip manufacturing challenges. The co-packaged optic is sort of a final kind of integration point where you're combining more directly the ASIC and the silicon photonics on a co-packaged substrate, usually with some sort of interposer, and kind of giving the highest level of connectivity and the highest level of density. Okay, next slide. Okay, and I just wanted to kind of on the last two remaining slides, just talk about some of the fiber technology trends that we're starting to see in a little background. So Keith, obviously, in his presentation, talked about a very dense single mode fiber solution where there's some version, AFL solution is a spider web ribbon, but basically some sort of rollable solution where you can get these very compact cable densities. Okay, and what's shown on the right-hand side is a 576 fiber, this 12.4 that Keith talked about. There has been some significant trials on multi-core fiber, in particular four core. So that's four single mode cores within a single fiber space, 125 micron clad. And when you start following that logical extension, if you start reducing the number of fibers, okay, say to 144, but you're keeping the same number of cores, you can get a substantial reduction in cable size. Okay, there are trade-offs with that. The splicing obviously is a little bit more challenging because you've got to align the four cores on that piece, and the connectorization obviously is more challenging. And we're starting to see a lot more, especially between data centers, implementation of hollow core fibers. Kind of the current state of the art is probably this nested anti-resonant nodeless fibers that has good loss. But there are some challenges with that just in terms of the splicing and termination, but it does give good benefits about reducing latency, between the interconnection points. Okay, I think the last slide that at least I would cover is kind of on the technology piece. Okay, and you're starting to see. Along with the increased cable density, different higher density connector solutions. So I'm kind of breaking it up into, three different areas, right? So there's the multi-fiber epoxy polish, your physical contacts connectors. So your traditional connectors that where the fibers are coming to physical contact. So the MPO or MTP is being displaced by the MMC and then the SNMT. I think there's probably a wider adoption of MMC, but SNMT is also a solution. The left-hand side showing the MMC, the right-hand picture on that row is showing the SNMT. There's also, in the spirit of decreasing deployment time, an evolution of expanded beam connectors. So instead of physical contact, the signal on the fiber is expanded and collimated, and in order to connect with maybe better dust immunity. So the solution that's being deployed now is kind of goes back to the 3M EBO, and US Connect is following with its PTMT solution, which will probably be out next calendar year. And this is also driving in the spirit of density with different equipments of ganging or combining these physical contact ferrules and expanded beam ferrules into different connector formats, either on the front of the panel, mid plane, or back plane, in order to improve the connectivity and in a lot of cases enable the use of co-package optics. Okay. So Antonio, I think you have the last slide before we switch to questions.
Yeah, thank you, Ted, and thank you, Keith. I'll be brief, but hopefully this helps understanding why AFL's role is critical on the AI infrastructure. We provide the expertise and the value end to end to that one layer that determines whether a multi-hundred-million-dollar cluster is actually going to deliver structured near zero loss, ultra high density fiber backbone compute power. Kelly, thank you.
Thank you.
Over to you for questions. And sorry, we are running a little bit of
That's
time. I
okay.
probably talked too much.
Don't worry. Don't worry. It's one of the trials and tribulations of being completely live. So our audience knows it's not pre-recorded. We're definitely live. It's all fine though. We can overrun ever so slightly. So no problem. So, just before we start taking your questions, I'd just like to say thank you very, very much again to Antonio, Keith, and Ted for sharing your insights with us and your presentations. It's really, really interesting stuff, and it's really exciting times at the moment as well. So, thank you ever so much. I am going to start with a question about the demand for AI training. So, can I ask, how big is the AI training demand wave? And is it real, or is there a degree of hype towards it? Who'd like to take that one?
I can probably take that one, Keith, if you want to contribute as well. The McKinsey model told us that the training compute power out there is tripling, right? From 23 gigawatts to 62 gigawatts by 2030. And that deployment is happening today and is being built today. So it is very real and it's going to be very much required to train the AI models of the future.
Yeah. I think that what's really important, what we're seeing now, is the training the training clusters over the last year really have just grown and grown and grown, and the demand keeps on growing. But you have to view training as an asset that you invest in. It's a cost to the whole AI industry. And then once you pivot to inference, that's when you start to monetize it. So in the same, this presentation was mainly on training, but in the same McKinsey slide, I think from memory, the training grew from 23 up to 90 or something. Or sorry, the inference grew from 23
Inference,
up
yeah,
to
yeah,
90.
correct.
So it's inference that will monetize it. And in order to have the best inference, you have to have the best model behind it. And in order to have the best model, you have to have the best training cluster. So the training cluster is being driven by the adoption of inference and the quest to have the best inference. And personally, I've seen huge differences in what you can do with Copilot versus ChatGPT versus Claude. And that purely is down to the models that sit behind the inference. I hope that answers it.
Thank you.
But it's definitely not going away anytime soon. That's the critical thing.
Yeah, absolutely. No, it definitely doesn't seem to be. We've had a question come in. I don't know who'd like to take this one. What schemes are available for fault finding and replacements?
I can start with that one.
Thank
So
you.
for fault finding, I mean, as I said, generally the fiber infrastructure is the last thing to go in, and the pressure to get it done like yesterday is immense on us and the contractors. And the other thing we've seen, especially in the US, is we're constantly being told by all of the hyperscalers that we have to design our products so that somebody who was flipping burgers yesterday can install our fiber today. So they want
Okay.
it as idiot-proof as possible. So we have to make it as idiot-proof, but you still have to clean it and you still have to test it. So we've developed the AFL test and inspection group. We've developed a 16 fiber tester that tests a 16 fiber. Everything now is 16 fiber links inside of a big AI data center with MMC connectors. So we can test a 16 fiber MMC in about 5 seconds for all 16 fibers. So you can test a lot quicker. There's now also been a kind of unwritten rule in AI data centers that everything gets installed with a 8+1 mentality. So if you take a 32 port switch, and if it's a 800 gig, well, then you have 512 fibers in that switch. So with your 8+1, it just means instead of installing 8 fibers, you install 9 fibers. So instead of installing 512 fibers, you install 576 fibers. And that goes all the way down to the NVL72, believe it or not, is actually 64 live GPUs and 8 spares, which is the 8+1 rule. So for fault finding and fixes, the fixes is generally if a connector doesn't work, you use one of the spares. So we install an 8+1 sparing rule. And then if you have more, well, then you just overlay a new 144 fiber trunk or a 576 fiber trunk. It's it's all about speed of a repair as opposed to trying to troubleshoot and fix individual connectors in the field. You wouldn't do. You just put a new one over the top.
Yeah, maybe to add to Keith's point, I think this is also driving why the industry is evaluating maybe some of the expanded beam connector technologies, such that if you do some of the connections, it also helps with potentially you have less likelihood of damaging connectors during installations. Also, maybe this also anticipates one of the questions as you make the transition from pluggable optics into co-package optics. That pluggable optics obviously can be exchanged. Okay, as you start adding things to the boards, that's going to drive a much higher reliability need kind of monitoring on the equipment to see that the quality of service is maintained for those transmissions that are co-packaged optics, and basically a higher level of certainty that the equipment is robust before deployment.
Brilliant, thank you. We've had a question come through about skills. Unsurprisingly, with the technology changing and moving towards AI, there's a lot of kind of talk about the skill set. So this person has asked that they want to better understand the overall level of the labour force demand in terms of expertise in areas such as structured cabling, insulation, fibre splicing, and people's knowledge of network technology such as switching and routing. Have you found that there's been a difficulty in this area to find skilled professionals, or what are your views, guys? Who'd like to go first?
I'm probably closest to it on
I was
kind
going to
of
say
daily
same, yeah.
basis.
Okay.
Yeah.
Yeah.
In the US, it's a major issue. I mean, splicing inside the data center. There are areas that you can splice if you're running between buildings and you have to get through ducts. Splicing has a place, but if anyone is going to be splicing connectors or splicing cables inside the white space, that's just crazy. You want to make sure that you pre-term as much as you possibly can, and preferably pre-term with the highest possible fiber counts you can. Um, but in the US, it comes down to what I said earlier. It's all of the hyperscales say to us that the people that are installing our fiber, we just have to acknowledge that they probably or quite possibly have never touched a fiber before. So skilled labor availability is a major issue. As I said earlier, the only thing that's not constrained in an AI data center is space. Everything else is constrained. The fiber is constrained. The labor is constrained. And so in Europe, we haven't seen the wave take off as much as we've seen in the US over the last sort of 18 months. I do expect this year we're going to see some very large deployments start to kick off, and in 12 months' time, the labor demand in Europe is going to be huge. But it also then just separates the kind of skilled labor that is in place today. They become more valuable because they are skilled, and then the things like pulling cables and dressing cables becomes the unskilled. So it's the demand is going to grow in Europe massively, and if there will be a skilled labor shortage, and then the skills of people splicing between buildings becomes a pretty expensive commodity.
Yeah. Thank you for that insight. Did anyone else want to add anything at all?
No.
No?
No.
That's all good. You don't have to. We are running out of time now, I'm afraid. If you have any questions and we haven't gotten around to answering them, feel free to send them on, and we'll pass them on to our lovely speakers post-webinar. So please don't worry if we haven't got around to your question. On another note, if you would like to receive a certificate of attendance for this webinar, please do get in touch with us. You can do so at the email address where you logged in, the production@europascience.com email address. So please feel free if you'd like your certificate. All that remains for me to say is thank you very, very much again to Antonio, Keith and Ted. Thank you very much to AFL, our sponsor. Thank you to everyone who's joined us today and who sent their questions in. We really do appreciate your interaction and engagement with us. Thank you very much to our production team and to David, who worked hard in the background, making sure that things go off without a hitch. This webcast will be available for 12 months on the Fibre Systems website. That's www.fibre-systems.com. And as I say, don't forget to ask about your certificate of attendance, and don't forget that the Q&A obviously will not be live, will not work on the on-demand version. So all that's left for me to say now is thank you very much to everybody again. Thank you for joining us, and we'll see you at the next webcast. Thank you. Goodbye.
Thank you.
Bye-bye.